Hello and welcome. So today we are going to discuss a very interesting and important aspect, that is about electric field and electric potential. Now, what is the difference between them? And these two concepts are very important not only for electrostatics, but they are also equally important for the chapter gravitation. So today I am going to give a trick how I relate them. If we take a charge Q, now this charge Q we will say is the subject charge. And now we are interested in calculating the electric field due to this charge at a location R. Okay. So we define the point here. Now we define electric field as the force experienced by a unit test charge small q. Okay, so our subject charge is big Q and our unit test charge is small q. And since we are interested in calculating the electric field due to the big charge, what we are going to do is we want the smallest influence of test charge q. So we are going to put a special definition, limit q tends to 0. All right, because we are interested in only the field of big Q. So this is how we set up the electric field. Basically, electric field is a special kind of physical quantity which multiplied with the test charge Q gives the force. Now, the concept of electric field becomes important when you have complicated shapes or you have collection of charges. Okay, so let's go on, and then we write down using the Coulomb's law. The force will be given by 1 by 4 pi epsilon naught big Q times the small q divided by r square. Now this is the Coulombic force, and we are going to divide this force by the test charge. All right. So from this, what do you get? Is basically 1 by 4 pi epsilon naught q by r to the power 2. All right. So this is how we define the electric field. Now, electric field should also have a direction. Because of this positive big charge, the electric field will be in this direction. Now, let us denote this direction with the unit vector r. Okay, so we are going to put the unit vector r. Now, this unit vector you can easily obtain. All right, so electric field is a vector quantity. Now, let's move on to what is called electric potential. Now, we define electric potential at the location R as the total work done. Okay, work done to bring an object from R is equal to infinity to a position R divided by the test charge. Okay, so the electric potential due to the big charge, I'm going to put the subscript big Q, is basically the total work done required to bring this small charge Q. Now, on our board here is the infinity. Now, we bring this charge taking any path to a location R. Then we define electric potential as total work done divided by the test charge. All right. Now, let's do the calculation of this work so that we can get the formula for the electric potential. Okay, so suppose here is our big Q. Somehow we have moved this test charge at a location R. Okay, from infinity to this position. Okay, and potential only depends on the position but not the path taken. Now, why it is so? Because we define potential energy and potential only for the conservative forces. And here we have the electrostatic force. And similarly, if we have the gravitation, we define the potential for only conservative forces. So total energy in case of conservative force is conserved, and we can define potential in this manner. So let's get down to the task. Now you can see if this charge Q is at a position R, it will feel a force. Now the force will be repulsive, will be in this direction. Now what we are going to do is we are going to calculate total work done. Now in order to do the work done calculation, first let us look at the force. Now force as compared to the location depends in this manner, right? It's the Coulombic force. So force is inversely proportional to R square. So this is no more a fixed force. Since this is a variable force, we have to consider the area under force versus displacement curve to calculate the work done. Now we are bringing this charge from infinity. So infinity is somewhere far away. Suppose we are going to bring it to a location R is equal to big R. Then if we are interested in calculating the total work done, then we have to calculate the area under this curve where this point goes to infinity. Okay? It is no more constant force. Okay? It is inversely proportional to R square. So we have to use calculus. Now, in order to solve this problem, what I'm going to do is I'm going to say I have brought it at a position R, and now I'm going to move it a little bit towards this big Q. Okay? Now let's call this displacement as dr. Okay? Dr means it's a very tiny displacement. Now corresponding to this, our work done will be dw is equal to F dot dr. Right? Now dr is also the vector. We write dr vector as dr times some unit vector. Suppose we take a unit vector along this direction as r cap, then in the inverse direction we will have minus r cap. Okay? Or we can look at the force. Force is in this direction while the displacement is in another direction. So the angle between force and the displacement is 180 degrees, right? So from here what we can write down is F dr cos 180. We already know cos 180 is minus 1. Okay, so we can write the tiny work done is equal to F dr times minus 1. Alright, until here everything is clear. Okay, now let's rewrite this work done, the tiny work done, we can write down as the Coulombic force and dr. Right? Now we are going to calculate this force to bring this charge from R equal to infinity to R equal to big R. Okay, big R is some location. Suppose big R will be somewhere. Okay, that is the final position we have to arrive. Now, the total work done, we can write in this manner where we have to integrate R equal to infinity, the initial position, to R equal to big R. Now, I have changed to big R because it will be a beautiful expression. Okay, so this work done is going to be 1 by 4 pi epsilon naught Q times Q, right? And then you don't have to worry, we have very simple integral, R to the power minus 2 dr. Okay, now why we are integrating? Because we are calculating area under the curve, and since the curve is not constant, we have to use integration. Okay, now if you look at this integral, this can be easily solved because we know z to the power n integral dz is equal to z to the power n plus 1 divided by n plus 1 plus some constant, all right? Now, this relation is for indefinite integral, but here we have a definite integral. Now, this definite integral says our r changes from infinity to r equal to big R, right? So, we can clearly write this term as q by 4 pi epsilon naught, and then this will become, we forgot minus 1, right? Because there was always a minus 1. We have to be correct with the sign. Here it was minus 1. So then this will become r to the power minus 1 divided by minus 1. And then we have to put the first limit and the second limit. Okay? So now we have found the total work done to bring a particle to a location r. We brought it from infinity to this point, right? We take the big Q out, and then we write it in a special way. Q by 4 pi epsilon naught, and this is r to the power minus 1. That means that is 1 upon r minus 1 upon infinity. All right. Now, if you see this expression, you can already see the definition of potential that we were after. So you can write Q times Q by 4 pi epsilon naught into R minus Q by 4 pi epsilon naught into infinity. Right. Now, we already know this potential here is visible. Okay, so we can rewrite this as Q times the potential at a location R, that is this, minus the potential at the location infinity. All right, now you can clearly see we define potential as the total work done to bring the charge from infinity to a position R as work done divided by the test charge. Okay, you can see the test charge is here. You can see V infinity is 0, which is taken as a reference, and VR is the potential. Now, comparing these two formulae, what do we get? We get the potential V at a location R is given by 1 by 4 pi epsilon naught times the big Q and 1 upon R. So you can see we have obtained very beautiful expression of the potential. All right. So you don't have to remember, you can just follow the logic. Okay, so the next thing I'm going to do is I'm going to relate the electric field and the potential. We basically know the electric field is a vector quantity, and we just derived that the potential is given by this formula and is a scalar quantity, because you can see here work done is a scalar divided by the charge, which is again a scalar quantity. All right, so now every student is often puzzled, how can we relate a vector quantity with a scalar quantity? Okay, so the way to relate them is by using the definition of work done. So let's do quick calculation. The small work done, we already know, is F dot dr. Right? And we also define work done is the charge times the potential difference. So if we move the charge Q through potential difference V, then we just multiply charge with dV and we get the work done. Now you can see here the force due to the big Q charge on the small q charge is in this direction, movement of this charge in opposite direction. Therefore, the angle between F and dr is 180 degree. Okay, so we can write down this F dr cos 180 is equal to Q dV. Okay, where dV is the potential drop. If we open this force F, we can write it is the charge Q times the magnitude of the electric field times dr, and then there is a minus sign. Okay, then this should be equal to Q dV. Okay, so we can write down our electric field, its magnitude will be minus dV by dr. Okay, so this is how we represent the magnitude of the electric field. Now the second puzzle is, how is electric field, which is a vector quantity, related to potential, which is a scalar quantity? The secret to the relation between electric field and potential lies in this relation. We basically write it as minus times the 3. Okay, minus sign we already know, because E and dr will be in opposite direction, because you know the force is repulsive. And this delta, this is an abbreviation which is a vector. So this delta is a gradient operator. Now gradient, you can understand when you are falling through a cliff, you know, or you're moving down a cliff, you have a gradient, and gradient has a direction. Okay, so gradient is basically the derivative d by dx I cap plus d by dy j cap plus d by dz k. All right, so in a brief manner, what do we write is okay. So you can look up the book of H.C. Verma. There is a very interesting problem in the numerical part, also in the solved example, where the relation between electric field and potential difference is exemplified and done very nicely. Thanks a lot for your attention. I hope you understood this concept. If you like more such videos, please like and subscribe.